Let's now discuss the structure of benzene and what is special about benzene. Benzene is a compound that contains a ring with 6 carbons that are joined together by alternating double and single bonds. There are 2 resonance structures for benzene that we can get from moving these pi electrons around the ring. On the left, we see that there is a double bond between these carbons, but if we move those electrons here, we would create now a double bond between these 2 carbons. That would force every other double bond to move to the left in a clockwise fashion to create this second resonance form. In these structures, we have a bond that in reality is not a single bond or a double bond. It's actually a bond and a half when we average out the 2 resonance forms of benzene. The true structure of benzene can be thought of as looking something like this, where there is partial double bond character in between every single carbon-carbon bond. Each carbon is sp2 hybridized in benzene and has a p orbital that forms a pi cloud that is both above and below the plane of the benzene ring. This is illustrated here, where the p orbitals are adjacent to each other on each carbon, and the top lobe on each p orbital will overlap so that there is a pi cloud here on the top of the benzene ring, but there is also a pi cloud underneath of the benzene ring. Experimental evidence has shown that the carbon-carbon bonds in benzene are about the same bond length. They are approximately 139 picometers, which is somewhere in between a typical length for a single bond and a double bond between carbons. The electron density in all carbon-carbon bonds is also identical, as well as the bond angles, which is about 120 degrees between the bonds between the carbons and also the hydrogens that are attached to these carbons. Hydrogenation experiments involving alkenes and dienes and aromatic compounds have shown the relative stability of these compounds. For example, cyclohexene, if treated with hydrogen gas and a metal such as palladium, would be hydrogenated and converted into cyclohexane. So in other words, palladium adds hydrogen atoms to this double bond to convert it into an alkane. The reaction leads to the release of 118 kilojoules per mole, since the reaction is exothermic. If we do a similar experiment with cyclohexadiene, adding hydrogen gas and palladium, the double bonds in this diene will be converted into single bonds, and therefore we will have cyclohexane. Based on the experiment from cyclohexene, we could theorize that the reduction of the double bonds in one cyclohexadiene should release about 236 kilojoules per mole. In other words, if we double this value, which is the release, the energy release from the hydrogenation of a single bond, we should be able to approximate how much energy should be released from the hydrogenation of 2 double bonds in this diene. When we do this experiment, we have found that the reaction actually leads to only 230 kilojoules per mole of energy being released. Since the product in both reactions, the reduction of this diene and this alkene, both lead to making cyclohexane, the difference in energy between these 2 reactions is based on the fact that a 1,3 diene has a small amount of stability due to the conjugated double bonds. In other words, we have found from this experiment and others that when we have a double bond that is alternating with a single bond and then another double bond, those two conjugated double bonds tend to be more stable than individual single bonds. And for this particular example, that stability is somewhere around 6 kilojoules per mole. This extra stability from conjugated double bonds leads to benzene having a stability of about 150 kilojoules per mole more than you would expect. So in other words, when we try to hydrogenate benzene, so in other words, add hydrogen gas and palladium to convert it into cyclohexane, based on the experiment we saw with cyclohexene being converted into cyclohexane, you would think that if we took this value and multiplied times 3, since there are 3 double bonds in benzene, we should theoretically release from the reduction of benzene into cyclohexane about 356 kilojoules per mole, just simply by taking 118 and multiplying it by 3. However, when this experiment is run, we find that the reaction only releases about 206 kilojoules per mole. The difference between the actual amount of energy released and the expected from tripling this value here is due to not only the conjugation between these double bonds, but also something else. Clearly, we can see from the example of this diene that having conjugated double bonds adds a little bit of stability to the compound. But that was only about 6 kilojoules per mole. In the case of benzene, we see a huge amount of stability, and this is due to something that scientists like to refer to as aromaticity. So in benzene and other similar aromatic compounds, there is something special about them in terms of stability that leads to a very strong and stable ring. In the case of benzene, it's approximately 150 kilojoules per mole.